Hi, this video is an introduction to quadratic functions, chapter 9 in our algebra book. The first thing I want to talk about is how much there is in common between our linear functions that we learned in chapters 4 and 5 and these quadratic functions that we're learning here in chapter 9. First of all, you'll see here on the board we have our function machine. We have x for our input, y for our output, and the rule on the inside of the function machine is ax squared plus bx plus c. If you remember back in chapter 4 when we talked about rules for function machines, we had any type of x value in there, added, subtracted, multiplied, divided. It was just an order of operations. When the x input went in, it fell into its spot in the x location there and then spit out the output y. This is no different. Just with a quadratic function, we have a degree of 2. So that ax squared plus bx plus c should look very familiar from last chapter when we dealt with quadratic expressions. Now we're just moving into the equation mode where we have an equal sign, which means instead of simplifying or factoring, we are going to actually be solving for those x values. So when we started with our linear functions in chapter 5, we learned how to graph them. And when we graphed them, we saw these straight lines with constant rate of change. That was our slope. And now we are going to get what is called a parabola. So when we graph a quadratic function, it's going to look like this. It's either going to open upward or downward, and it's going to have a vertex. The vertex, that spot there marked vertex, is either a maximum or a minimum value for our quadratic solution. Remember, these lines that we graph are solutions to these equations. They are made up of ordered pairs, x comma y, that when we plug them into the quadratic function that we're working on for a particular problem, it gives us a true statement. Never forget that these solutions, again, these are made up of ordered pairs, two unknowns, x comma y. Each of these solution points, these ordered pairs, plug into this quadratic function and give us a true statement. When we graph these quadratics, we see a parabola. It's either going to open upward, and the vertex is either going to be a minimum, or it's going to open downward, and the vertex is going to be a maximum. Now going back to this guy over here, that axis of symmetry, that dotted line, splits the parabola in half. And in class I showed you, I folded a piece of paper with a parabola on it, and it folded right on the vertex. And again, that dotted line, the fold on the paper, that is the axis of symmetry. It goes through the vertex. The axis of symmetry is an x line. The example up here in front of you is x equals -5, that vertical line, the axis of symmetry. If you remember, we used the vertical line test back in chapter 4 when we were talking about whether or not something was a function. So we should be very familiar with vertical lines. This vertical line, again, the axis of symmetry, cuts the parabola in half and serves as a point of reflection. We'll get into that a little bit more later. What's important to understand now is that the axis of symmetry goes through the vertex, and we will be calculating a value for the axis of symmetry. We'll be finding that x value for that line, and that then becomes the x value for our vertex. Hopefully you can figure out how we would get the y value for the vertex. Think about that for a second. If I know the x value for a solution to a quadratic function, I should be able to plug in that x value into that quadratic function and get my y value for that x value, right? So that would give me the y value for my vertex. And again, we'll be doing that later. So let's keep going here on this parabola and what this depiction of the solution, what this graph looks like, what it tells us. Remember, a while back we learned that another word for x is domain, another word for y is range. The range on a quadratic function is limited. If you look at our maximum value here up top, that is the highest number for y in this particular solution. There are no y values in this solution any higher than that vertex. And if you look at the second one, the minimum, that range is limited. There is a minimum value for the y in that quadratic function. There are no y values lower than that minimum value there on that quadratic function there in the bottom. The domain, however, the x value, is not limited. Now it's difficult to imagine, but that parabola, whether it opens upward or downward, continues to get wider. So eventually every x value will be covered from left to right. Every x value will be covered. So the domain is not limited, which makes sense if we look back at our function machine. Remember, we learned about our functions. We said that input is what we decide. We decide what we put in the function machine. We decide on the raw material. We decide on the input. So there is no limit as to what we can throw into that function machine. That is part of the reason that our parabolas and most every one of our linear equations had infinite solutions, right? Those arrows on the end say it goes on forever and ever. Now, we have a little star here, and we just need to remember that sometimes limits are used for our domain. For example, story problems. And the example I use in class is, if you remember linear equations, we would put limits on our x value if we were talking about people or money or pizzas. We can't have half a person, half a pizza. We can't have a negative person or negative pizzas. So sometimes our domain is limited, but those are situations in story problems. And then we do have a control or some input that we have very specific numbers that we want to choose. All right, let's talk a little bit now. We're still on the parabola, but looking at the equation, how do we know what our parabola or our solution point will look like? So first of all, ax squared plus bx plus c, again, our standard form for our quadratic. That a is our leading coefficient. We learned that last chapter. If the leading coefficient, if the a is positive, the parabola is going to open upward. If the leading coefficient is negative, the parabola is going to open downward. You'll be asked to compare parabolas and tell whether it's going to be wider or more narrow than another parabola. The way to remember this is the smaller the a, the smaller the leading coefficient, the wider the parabola is. So I think of it as short and stout or tall and thin. If the a is a large number, it's going to be pretty tall. It's going to be pretty thin and narrow. If the a is a small number, it's going to be kind of short and a little stout, a little bit wider. Let's look at a few examples.